All right, so we're going to talk about the mass energy equivalence, which was introduced by Einstein in this lesson. This is that crowning moment when your high school physics education has now led you to learn about E equals mc squared. Um, Basically, we've switched our view of space and time and mass from classical physics to now relativistic physics. Right, so we've changed time, we've changed space. Right, we've got all these different things, and now we've also changed mass. That was last lesson. So because we've changed all these things, we now have to change the way we think about momentum and energy. Right? So momentum has to do with mass, and energy has a lot to do with distance and velocity, and there's also mass involved in energy. So there's a whole bunch of things. So let's look first at momentum, and let's talk about relativistic momentum. So in classical physics, we knew that momentum equals mass times velocity. Okay, so this is obviously going to change now because we have mass which dilates when we get close to the speed of light. So if I make the substitution in momentum for dilated mass, I get P is equal to m naught v all divided by 1 minus v squared over c squared. Okay, so this is what I get. And it's like, yeah, okay, no problem. This is relativistic momentum, right? So we use this law whenever the concept of momentum or its conservation involves relativistic speeds. So that's it. It's as simple as that. We basically just put this dilated mass into this equation. So let's take a look. An electron is moving pretty fast, 0.75 c. What's its momentum? And then let's compare that with the value calculated from the classical expression. So here's m naught, the rest mass of an electron, 9.11 times 10 to the minus 31. And here's how fast it's moving, 0.75 c. So classically, this is what we would say. Momentum equals mass times velocity. There's the mass. Here's the velocity, 0.75 times the speed of light. And we get 2.04 times 10 to the minus 22 kilogram meters per second. Okay, pretty easy. Relativistically, though, it's a little bit different. We've got m naught v, but we have to divide by this gamma, right? So we have to divide by this factor that corrects for relativistic speeds. So when we make our substitutions, we've still got our 9.11, we've got 0.75 times the speed of light, but we're now dividing by this factor. And what we end up with is 3.10 times 10 to the minus 22 kilogram meters per second. And this represents, of course, more momentum. So because mass increases when you go faster than the speed of light, so does momentum. Momentum also gets bigger. So if we don't take this into consideration, we, of course, end up ignoring a large piece of this momentum. This is very, very important when you start talking about things like particle accelerators and collisions at the atomic level, when things are moving super fast. All right, let's turn our attention to energy. And it would be really, really nice if we could do the same thing with energy that we did with momentum, but we can't. Okay? So we know that the change in mechanical energy of a system is called work. And if we do work on an object by applying a force, we can change the object's kinetic energy. So when we're working with relativistic speeds, we need to modify our equation for energy as well, right? Because we're doing work on it, and we got to change all these things around. The true derivation of the expression that we're about to do is much more complex, and we're not ready to handle that, especially not in grade 12 physics. We're going to deal with a derivation that it's valid, but we're going to assume certain things, and we're going to avoid certain unnecessary mathematics. It's certainly less it's less elegant, right? And so, this is a valid derivation that we're going to do here. It's less elegant than what it should be, but that's okay. For our purposes, it's fine. So, due to the fact that mass dilates at high speeds, it might be tempting to simply change our expression for kinetic energy, the same way that we handled momentum. But let's use Einstein's mass energy equivalence, E equals mc squared. Okay, and we can make a substitution for this dilated mass, right? So we're going to start with Einstein's E equals mc squared, because after all, this is what he said: the energy of a system is equal to its times the speed of light squared. Okay, so here's our dilated mass, and we're going to make this substitution in here. And, well, once we have this, there's this thing called a binomial expansion. And in a binomial expansion, we can take a term like this, 1 over the square root of 1 minus v squared over c squared. And there's math to show us that we can change this into something that looks like this. Right? We can actually change the form of this into something that looks a little bit different. And the reason that it's valid is for reasons that we're not even going to go into. So you just have to assume, okay, yeah, this is a neat little binomial expansion. It's a trick you'll learn when you get into calculus in university. And so using that, we come to this expression right here, that E is equal to m naught c squared times 1 plus v squared over 2c squared. And we can even make this more simple, that E is equal to m naught c squared plus 1/2 mv squared. And this right here, if this is the rest mass of our system, this is an expression that corrects for the energy of a body moving close to the speed of light. So Einstein called this term the m naught c squared term, the energy that an object has while it's at rest, or its rest energy. And so the total energy that exists for an object is the combination of its rest energy and its kinetic energy. So let's take a look at this. An electron in a television picture tube typically moves with a velocity of 0.25 c, so a quarter of the speed of light. What's its total energy and its kinetic energy in electron volts? Well, we know the speed that it's moving at, and we know what its rest mass is. And so we can find out its rest energy, E naught, by saying m naught c squared. And this translates to 8.199 times 10 to the minus 14 joules. We can, of course, change this into electron volts. You haven't seen this yet. Look it up in your textbook, and you'll know it's just a conversion. Electron volts are a way of expressing very small energies in terms of something a little bit more palatable. The kinetic energy of this system is 1/2 m naught v squared, right? Which is, of course, 1/2 times 9.11 times 10 to the minus 31. And then we take the speed of light squared, or we take the 0.25 times the speed of light all squared. And we can work this out, and this is 2.562 times 10 to the minus 15 joules. And we can add these two energies together, and we get, in terms of electron volts, 5.12 times 10 to the 5th plus 1.6 times 10 to the negative 4, which is a lot of electron volts, but not very many joules, right? So this is basically how we're going to do that. And so this is a crash course in the very beginning of relativistic energy. If you want to know more, please take a look at some of the minute physics videos for E equals mc squared on YouTube, and also take a look at some of the other E equals mc squared videos. There's some very good ones out there, and they're not too confusing.